This is the arithmetic logic unit course project demonstration for the binary bandits. We have done 12 of the all 12 required gates, including 2 bonus ones, being the Johnson counter and the shift rotate. I will be starting with going from and to even logic units before handing off to my partner. Starting with the AND operation at code 000. Let me quickly set this. Operation code 0000. We start with our bitwise AND. As you can see, all zeros, it'll pass straight through. But once we switch one and we get a matching one on our A's and B vectors, once they match, passes through. Likewise with each bit. Like I said, this is bitwise. And next, our OR on operation code 0001. On operation code 0001, we have our bitwise OR, which means that either side will pass the respective bit through in any case, or if you switch them both on, the expected behavior occurs where it's the standard, where it's the same as if one was on, as expected from a basic OR. And then you can also combine them, and they're the same expected behavior. Next, XOR. This will be on the operation code 0010. So for example, testing some of our test cases to show this example, you pass all ones, you will get F out of A when it's because it's not matching your zeros. As you can see, functions similar to the OR gate as expected, but once you've got your matches, actually wait, is this, should be, yep. So with our XOR, we've got our codes passing through, likewise. A bitwise fashion, and it will go to 0 once you have both of them combining to conflict. They cancel each other out. Now, next up is our bitwise inverter. This only operates on the A vector. Switches here. And this will be code 0011. As you can see, as soon as we turn on the inverter, immediately flips our switches, which are set to 0, and outputs them as if they were all 1 as expected. And if we do the opposite, 0 with these being while they're high, providing the inverse of the standard output would be when represented through hexadecimal. Next, we have implemented a full ripple carry adder, or a full ripple carry addition with our adder, including carry in support, which has not been marked, but it is bound to switch, or sorry, not switch, key 1. So if we pass, opcode first, 0100. As you can see, on key 1 we have our, phone slid a bit. On key 1 we have our carry in as shown. And if you see, it might be hard to see, I'll tilt the board so it's more easily visible. But if we, for example, do 8 plus 8, you will see that it overflows and allows us to add additional characters from the digits from the following switches. And our overflow will actually be represented with this red LED, which you might be having a hard time seeing because it's underneath this sticker that's right here that indicates our carry out. So once you see when we are not overflowing, carry out's gone. Now, our comparator. For our comparator, we will be on opcode 0101. So for this case, you can see when both of the vectors are equal to each other, you'll see E for even or equal. When one of them is greater than the other, its respective letter will appear. So for example, if we have more A is what appears. If we have more of B, then B is what appears because that's the dominant vector because it's greater than it. And if they are equal, no matter what the number amount is, E will be represented to represent that. Now, next up is our odd checker. And the odd and even are quite interesting. I enjoy their simplicity because all you have to do really is check the least significant bit of the input to determine whether a binary number is even or odd, which makes it map out in an interesting way in the actual design when you're doing it on paper, when you're mapping like direct active highs and direct like ground. So in this implementation, you can see if we do let me get the switch opcode. Okay, there we go, 0110 for odd. Now, so it will display F if it is false, and it will display O for odd if it is an odd number. This operates only on our A vector. So for example, as you can see, since it's 0 is an even number, so it displays false. 8 is an even number, it's false. 4 is an even number, false. And as you can see, no matter how much I change these, nothing changes because all of these are multiples of 2 in binary. But this is the switch that matters the most because that actually determines whether or not it's even or odd, because this is the least significant bit and only this is by 1. It's being a bit glitchy. There we go. Now, if we go on to our is even, that will be opcode 0111. So I'll hold down both buttons this time. As you can see, E is for even, it's even. And then if we do, as I said, any of the multiples of 2, it remains even. But as soon as we touch that least significant bit, as expected, false, because we are now presenting an odd number. My partner will now take over to showcase the sequential designs.
All right, moving into our sequential designs first. So the sequential designs, they all rely on a clock, and pretty much we have a clock 50 megahertz going to our clock divider that outputs 2 hertz in order for us to actually see it on the hex display up here. So for our first one, we're only using the A vector. We have a load that loads the A inputs, and if it's not loading, then it's shifting right. We also have a push value, whether or not we want to push in a 0 or a 1, and then we also have a reset, who I'll show you here in a bit. So for the opcode, it should be 8, and right now we're not pushing in anything because it's pushing in a 0. So right here, whenever I push it to 1, it's pushing in a 1 from the most significant bit. Eventually, it fills out everything to F. Showing one of our test cases here, 0101. It should display a 5 right now, and then once I start shifting, it should go from 5 to 2 to 1 to 0, as I'll show here, as you can see. And then for our next one, I'll be doing 000, loading that value in. and I'll be pushing in a 1 this time. So it should be display a 0, an 8, a C, an E, and an F, as you can see right here. And then just showing our reset working, as you can see. Okay. And for our last test case, 0, 1, 1, 1, 0, 1, 1, 0, pushing in a 1. This should be outputting 6, B, D, E, and F. So once I let this go, D, E, and F, and just showing our reset. That's pretty much how it works. Essentially, moving on to our shift left, which instead of pushing in a value from, sorry, the board.
I just fold the paper.
That's fine. Essentially, instead of pushing in a value from the most significant bit, we're going to be pushing in a value from the least significant bit. And essentially, we're still using only the A vectors. And for the B vector, we still have our load and our push value, which is essentially the same. So for the opcode for the people shift left, it would be 1001, as I'm holding it up here. And for our first test case, 0101, loading that up, we'll be pushing in a 0. So once I let this go, it should be a 5, A, 4, 8, and 0. As you can see right there. Moving into our next one, it'd be 10, 10. We're going to be pushing in a 0. And once I let the load shift go, it's going to start shifting to the left. So it'll start at A, 4, 8, and 0. As you can see right there. And for our last one, we'll just be pushing in a 1 whenever it's all 0. So it should be 0, 1, 3, 7, and F, as you can see right here. And then here's our reset working. Moving on into our next one, sequential operation. We'll be using, it's called the people bidirectional shift register, which is pretty much a combination of both the shift left and shift right. Essentially, we're adding one more input, which is the direction right here in the B vector, which pretty much decides if it's 0, which means it's off right now, it's going to be shifting to the right. And if it's 1, it's going to be shifting to the left, essentially. And as always, it's still using the 8 inputs, and it also has the reset over here, as you can see. So for this opcode, it would be 1010, which would be 10. So starting off with our first one, 1001 will be it'll be loading, it'll be pushing in, it'll be 0 as in shifting right. We're going to be pushing in a 1. So once I let this shifter go, 1, 2, 3, 4, it should be outputting, well, right now for 9, then C, then E, and F, as you can see right here, working phenomenal. Then our resetting it back. For our next test case, we'll be doing 0011, loading it up. Direction will still be 0, so shifting right. We'll be pushing in a 1 this time. So, yeah, pushing in a 1. So once I let this load shift go, it'll be outputting, well, for right now, 3, 9, C, E, and F, as you can see right here. Shift right's working as intended. Moving on to our last test case, 0101. We'll be loading it, and this time we'll be shifting left whenever I switch the direction up, and then we'll be pushing in a 0 from 5. So once I let the load shift go, it's going to be out, for right now, it's outputting a 5, and it's going to go to A, 4, 8, and 0. As you can see right here, showing our reset. All right, works as intended. Now, moving on into a different one, we'll be going into our bidirectional counter this time. Let me line this up. Our bidirectional counter pretty much counts up and down depending on the direction. So pretty much if it's 0, then it's going to be counting down. Or if it's 1, it's going to be counting up by 1. And essentially we have preset here, which is essentially the same thing as load, where we have it mapped to our least significant B vector. The counter also has a reset. So first, the opcode for the counter would be 1011. As you see right here, it's already starting to count down. And once it counts down, it should go all the way back to 15, which would be F, as you can see right there, working phenomenal. Testing our reset. So for our first test case, we will have the preset on. We'll be loading in 1100. So from there, we're gonna be having it counting down, so direction 0. It's gonna output C right now. It's gonna go from C, B, A, 9, 8, 7, 6, 5, 4, 3, 2, 1. Once I let this go. As you can see right there, counting down. Working well, and then once it reaches 0, it's gonna loop back to 15, which is F. Moving on into our next one, we'll be having F, this time counting up. So essentially, from F counting up, it should go straight to 0 once I let the preset go. As you can see, going all the way from 1, 2, 3, and 4, and 5. Going to our third one, which would be 0. As you saw earlier, this time we're going to be counting up. So from 0, we're counting up. It goes to F all the way to 0, 1, 2, 3, 4, and continuing forever. Our resetting it whenever we need it to. And that concludes the end of our 12 operations for the project. We'll be moving on to our bonus. Our bonus, which includes the Johnson counter and the shift rotate. The Johnson counter and the shift rotate still use the A input vector. They both have a reset and a load shift, a direction, whereas shift rotate has a rotate operation. We'll get more into that later. But essentially, the Johnson counter is pretty much, it's a counter, but I think of it more as a shifter. So if you shift right, the least significant bit is wrapped around and pushed into the push value, but it's knotted, which I'll explain here in a bit. So for the opcode, it'd be 0, 1, 1. As you can already see, it's already working. Since the direction is up, it's shifting to the right. So the input, the least significant bit is being pushed out and being put back in the most significant bit, but it's knotted, so it's inverted. For our first test case, I'll be showing here, we're going to be loading in 1, 1, 1, 1. Direction will be 0, so it'll be shifting right. So essentially from F, it's going to go to 7, 3, 1, 0, 8, C, and E. Once I let the load shift go, 7, 3, 1, 0, 8, C, and E. Working phenomenal. And then from 0, loading that in, 0s and shifting right, we should expect to see it being 8. From 0, 8, C, E, F, 7, 3, and 1. I can see right there. Here testing our reset. It goes back to continue counting. Working phenomenal. And for our last one, I'll be showing here 1, 0, 1, 1. This time our direction will be going up, so we'll be shifting to the left. Once I let this go, 0, 1, 1. So once I let the load shift go, it should be going to B, D, E, and 7. Oh, my fault. I was looking at the wrong one. I was looking at the shift rotate on accident. For this test case, it would be 0, 1, 1, 0. As we're loading this in, we'll be shifting right. It should go into 6D, A4925B. As you can see right here. Pretty great. Moving on to our last one, which would be our shift rotate. Essentially, this shift rotate essentially works the same as the Johnson counter. This time, instead of knotting what's being pushed back in, we're actually just pushing in the normal value that's being pushed out, whether it's the least significant bit or the most significant bit. So the opcode for this would be 1101. So for our first test case, it'd be 1011, loading that value in. And pretty much our rotate, I forgot to mention, if it's, rotate, if it's 0, it's not going to be shifting, it's going to be pushing in a 0, but if it's active 1, it's going to be actually rotating the values around. So pretty much whenever this is 1011, it's loading in and the direction is down, so it's shifting to the right, and then we're activating the rotate. Once I let this go, it should go from B, D, E, and 7. It's just shifting the bits around. Essentially, a pretty small loop. Loading in our next value would be 0, 1, 1. Already loaded in. This now will be shifting to the left, and the shifter is activated. So from this 3, it would go to 6, C, 9, and 3. As you can see right here, working pretty great. And then for our last one, it would be 1, 1, 0, 1. Our load is being activated. This time we're going to be shifting to the right. And then we're going to be pushing in, or we're going to turn our rotate off. So it's going to be pushing in zeros, turning off the rotate. So eventually it's got a 6, 3, 1, and 0, and turn off pretty much. And here's our reset. And that is the end of our ALU project.